That is the answer to this question. Why visualize? It took you about a third of the time. But it's not just about the time. See, it's also about consistency. If I took a piece of analysis and gave it to a bunch of people and they pick a number either 5 or 6 or 7, I don't need to do the analysis. I can just tell the people pick a random number between 5 and 7 and go with that. Why am I bothering to do the analysis in the first place? And if I've done the analysis, then why am I not doing something as basic as highlighting the answer for people to see and immediately get it? Why do I put them to a position where they have to guess that number and potentially get the answer wrong? Worse yet, get different answers across different sets of people. Thirdly, perhaps even more important than the consistency, is about how we look at numbers. See, we as a species have been looking at numbers for the last 50 years. We've been looking at text in earnest for about 600 years, ever since the Gutenberg press. We've been looking at visual imagery for millions of years, ever since we as a species have eyes. We are hardwired for understanding things visually. We are gaining the skills gently to understand things as text. Even narratives, audio, we've been listening to language for only 10,000 years. So our ability visually is an order of several orders of magnitude more than any other kind of ability, barring touch and sense and things like that, which have existed for even longer. So it's sort of like when a child learns to read, the child no longer has the ability to think of the concept as a full sentence. When a child is reading, the child is putting together letters to form words, words to form phrases, phrases to form sentences, sentence to form paragraphs. By the time the child has come to the second paragraph, he or she has no idea what it was there in the first paragraph. And then we'll have to go back and try and understand. We are like that when it comes to numbers. When we are presented with an array of numbers, we say, what is this number? What is that number? What is that number? Oh, okay. Which number was bigger? We are focused on trying to read the letters, not on reading the paragraphs and absorbing the meaning. Now, why do you want your audience to spend the bulk of their time trying to figure out what those numbers mean? You want them to be figuring out what they should be doing in the business. And data visualization is an absolute essential for that, because it has the ability to communicate the insight in the fastest possible way. On the other hand, this is not the only way. This is a talk about data visualization, so I'm telling you how great data visualization is. If this were a talk on narrative sciences, I will tell you how important narrating stories are and so on. The point is this: helping people understand data is critical. Data visualization has an above average role in that. I will confess that it is not the most important thing. However, in this particular talk, I'm only going to talk about data visualization. Let us dive in there. So what does it mean to say that I can get insights by purely visually representing data? Is there an example that I can show of something that has come up only because of data visualization, and otherwise just by number crunching I couldn't have figured it out? Several. Let me show you one of those. We had weather data from the meteorological department. They said, look, this is old data. I have the temperature of every single district for every single month starting from 1900 to 2000. So what can you tell us that we could not have already figured out? Fine, let's just plot that and see what India's temperature looks like without getting squashed. Okay, how do I unsquash India? Let's do one thing. I'm going to reload this video. Yeah. So this is what India's weather looks like if you plot all the hot areas as red, all the cool areas as green. Firstly, you'll notice that there are waves of heat flowing through the country, summer and winter. But some spots are immune. Kashmir is relatively cool right through the year. The west coast of India is consistently cool right through the year. Most of northeast of India is also cool right through the year, but summer and winter hit the rest of the country. But do you also notice one flashing spot where my mouse is? Flashing in the sense that it is hot when the surrounding areas are cool and cool when the surrounding areas are hot. This is a region that exhibits a countercyclic geographic pattern. And when we showed this to the weather department, we asked them, look, is this some kind of a data error? Are you sure you collected this data right? They went back, they checked, they found that the data is absolutely right. And they said, boss, we've had this data for a century, quite literally. And we absolutely did not know this. This particular region is Bilaspur in Chhattisgarh. It is an ongoing research problem to figure out why Bilaspur exhibits countercyclic weather pattern. We also find it to a slightly lesser degree in a region here, which is Shimoga in Karnataka. Nobody till date knows why this is, but nobody was even able to find it without having spotted it through this visualization. Why is that? Because nobody really thinks of doing an analysis of countercyclic geographic patterns. And what visuals do, among other things, is from an exploratory perspective, allow you to look for things that are easy to spot by the eye, but not easy to spot through mathematics. That's just one kind of pattern. Now, we can exploit this sort of a pattern from a technique perspective. See, on this graph, there are some things that stand out. A few things stand out more than others. Most likely, your eye would have been drawn to the plus that is out here. It just is quite literally standing out of the ordinary. But that's not the only thing that would have stood out. This one probably also stood out because it's in a different color. Some people have the ability to perceive color to a lesser extent. For them, it may not be so obvious. But to the vast majority, this would be relatively obvious. This X may also have stood out for a few people because it's slightly smaller, but it would have taken a little bit of time to get there. This may have stood out because it has a shadow. This is actually an O. This may have also stood out. And this one is potentially standing out as well because it's rotated. But for some of these, you'll have to actually closely go through. In fact, I'm sure I'm missing a few of these as well. You'll have to closely go through to see which ones are standing out and which ones are not. What that means is that some kinds of what I will call visual encodings or attributes are more discernible by the eye than others. And in fact, there is a hierarchy. So if I look at position, for example, that is pretty critical. Here is a chart that shows airline reservations. Now, it says that for this particular flight, the flight starts at this time and ends at this time. And this flight starts at this time, and there's a bit of a layover here and so on. Right? This actually just uses position to encode a huge number of data points. I know what the departure time is from this. That's the left edge of this. I know what the arrival time is. I also know the length of the trip by the length of the bars. And if there are stopovers, which we don't see on this particular screen, that is also shown as a variable. That apart, if there are stopovers, it also shows the duration of the stopovers. So from one flight to another, what is the gap between these stopovers, when they start, when they end. There is also price information that is based on the sorting of these. The position of these flights in order is used for sorting, and that's the y-axis that is being used. And what is the airline that is here? That is a categorical piece of information. But the thing is that the horizontal axis is capturing at least 5 distinct pieces of information which are interrelated but nevertheless distinct. And we are able to see this. Now, in some ways, you'd say, look, I am able to see a 5-dimensional visualization. But if you told somebody that I can create a 5-dimensional visualization, they say, are you crazy? 2 dimensions is bad enough for the scatter plot, right? Now, on the other hand, we've seen visualizations like this on a daily basis and we don't get confused. Now, why is that? Because the human eye perceives position extremely well and differentiates position also extremely well. If one of the photographs in this room were slightly tilted, we would have not the slightest hesitation in fixing it, and all of us would fix it consistently because we see misalignment very rapidly. Not all encodings are equal. Color, for instance, works in a very different way. If I look at this graph, for instance, now can you, by looking at the graph and without bothering to look at the legend, figure out which values are higher and which values are lower? Now, we have some sense of natural cultural connotation that red is perhaps lower, green is perhaps higher. But here we have white being even higher than that. That is not intuitive. We have blue, like cyan, being higher than that, which is greenish, and then blue and purple coming on top. Now, purple is actually a reddish shade. Why would one go for this kind of a scale? Or put another way, there is no natural order in color. Some kinds of derived orders can be imposed, lighter colors versus darker colors, red versus yellow versus green. These work in some cases, these do not work in some cases, but they can be very carefully applied and we can get a good color-based visualization. We can get it completely wrong. This is a case where I would argue that they got it mostly wrong. But there are elements, there are some regions where they've kind of gotten it right. A better use of color is something like this, monochromatic. Here there is less confusion. Darker is higher, lighter is lower. There may be confusion as to whether lighter is higher or darker is higher, but that is only one order of magnitude or one point of confusion that can be identified by looking at the legend. And once you figure it out, you don't need to look at the legend again. Colors are pretty good categorically as well. So, for example, if I wanted to differentiate between genders, pink and blue has the advantage that A, it is reasonably commonly used as colors for that particular gender, and just 2 colors we can easily differentiate it. If I'm looking at, for example, let's say nature, green is a commonly used color for anything that is natural and people can go for it. So if I take politics for instance, right, orange versus green, if those were the party colors, it does become easy. So in India, for instance, you would normally use saffron for BJP, and there isn't too much of a confusion because that is the party color. And so on for each of the respective parties, you kind of use the party colors. So where there is a set of categorical variables, there are relatively few, and they have some natural connotation to the user, then it makes all the more sense to use it. So these are two different ways of using color better. Now, what we've talked about is position is good, color is good if used in some ways, and so on. Is there a science to the whole thing? Well, yes, and you can check out this site complexdiagrams.com/properties, where there is a table of encodings which says that there are different kinds of values that you want to encode. There are different kinds of attributes or properties that you can use to encode these types of values. These work better, these work worse. What works where? Typically, for example, position is great for most things. But on the other hand, shape is very rarely good for most of the things. Differentiating between categorical variables, different types of things, position is a reasonably good thing. I could look at it the other way also, which is to say I have a set of quantitative variables. What can I use for it? First thing, exhaust all positional variables. Second, try and exhaust all text variables. Use length as a third option. Use size as a fourth option. Use angle as a fifth option. Use pattern density as your last option. By the time you get down to your last options, you are really scraping the bottom of the bucket. For example, there is a good reason why pie charts are a pretty bad representation. You'll find it very hard to differentiate between the size of two slices of pies, even if they are right next to each other. In fact, quite often you are likely to get it wrong. On the other hand, with two bar charts, you will have no confusion whatsoever as to which is bigger and which is smaller, no matter how far away they are placed, because they are fantastic with alignment. So there is just no question about what is better. Now, this is not, however, an argument saying that aesthetics does not have a role to play. Aesthetics has an important role to play. Sometimes if you create 1,000 bar charts, just tossing in one pie chart in the middle, even though it is less optimal, is good because at least the person who's reading through the 1,000 bar charts will not fall asleep. So there is a role for aesthetics. This discussion, however, is not about aesthetics, which is a lot tougher to teach in a scientific way than for something that helps people identify data visualizations and understand information better, which is much more scientific and easier to teach. What I want to leave you with is that there is a science behind how one constructs charts. Firstly, there is a science behind how one picks charts. You don't have to be restricted to picking charts, so you can create charts of your own, and that is largely based on a technique called the grammar of graphics. This talk is obviously too short to go into the details of it.